Alkaline membrane water electrolysis is very important in the HYScale project for several reasons. It aims to combine the benefits of the other electrolysis technologies like proton exchange membrane water electrolysis and alkaline water electrolysis while overcoming some of the limitations. Proton exchange membrane electrolysis operates at high current densities, delivers hydrogen with high purity and with high output pressure. But it needs to operate with highly corrosion-resistant materials like titanium bipolar plates and precious metals as catalysts like iridium and platinum. This is how the costs are rising for that technology. Alkaline water electrolysis, on the other hand, is more economical, but it also operates at low current densities, which is rising the system cost again. And this is where the anion exchange membrane water electrolysis wants to combine the benefits by operating at high current density while using no critical raw materials, and thus having a sustainable and economical system for hydrogen production. Critical raw material-free catalysts are crucial in the HYScale system to reduce both the cost of the hydrogen and the environmental impact. The catalysts inside the system do not use any critical raw materials or precious metals, and via that reducing the cost of the stack and the system a lot. Critical raw materials have a high environmental impact due to the mining and the processing of the materials, and to the scarcity of these materials should be avoided. And in the HYScale stack, via the use of critical raw material-free catalysts, we have the option to scale this technology and to produce the hydrogen in an economical way. Enhancing the low hydrogen permeability is crucial for improving the performance and the durability of the membrane. In this project, we want to reduce the hydrogen crossover via different methods. So the CEnMAT membrane ion flex, we want to include fillers or coat it with a nano layer. We did manage already to fill the membrane with fillers without losing any performance. However, there are challenges expected. For example, if you use fillers inside the membrane, it's really important to have a homogeneous distribution, to not create agglomerates of the filler and with that weak points which would increase even the hydrogen crossover. The same goes for the coating. This coating has to have a really homogeneous thickness to have the right performance of the membrane in all of the spots of the membrane. And to tackle that, we on the one hand want to improve the performance of the membrane by changing the backbone and the side chains of the polymer. And we are also monitoring the filling and the coating process really well via SEM and TEM measurements. And we also measure the hydrogen crossover in situ to monitor if the filling and the coating processes yield in a lower permeation of hydrogen in a good performance of the membranes. The main technological advancement of HYScale lies in its ability to perform at very high current densities, up to 2 ampere per square centimeter at voltages below 2 volt. This makes it possible to produce hydrogen at a 2-fold increased production rate compared to alkaline water electrolysis, which is lowering the system and the stack costs. Additionally, we do not need any critical raw materials. We can use stainless steel bipolar plates, critical raw material-free catalysts, and also can use diluted KOH concentrations, which is adding a lot of economical value and also sustainability, and which makes it possible to scale this technology. In the end, we then have truly green hydrogen, which we can produce at a levelized cost of hydrogen of €3, which is in line with the project goals and which is adding a lot of value to that technology.